uh, jumping in here to the agenda. Today, what we're going to do is really focus on autonomy. The panel we have here today, we're going to talk through things like why autonomy is important for corporations, some of the ways in which uh, autonomous robots and other kind of form factors can be used, some of the roadblocks and catalysts to seeing this come to reality. And we're also kind of going to go into one particular case study. So those are some of the highlights of what we'll be going through. And to kind of lead us through this session, we have Sophion, who's our technical director at Prescata, working with us for over almost a decade in the high-tech aerospace and defense area. So Sophion's worked with hundreds, if not thousands, of clients over the last decade, helping them kind of with their innovation challenges. And in that time has built a really strong acumen in understanding kind of the technologies in these spaces, as well as how they can be applied. He has a PhD in material science and engineering from the Georgia Institute of Technology, and is going to be a great resource for us today. So, Sophion, since we do have your kind of wealth of knowledge and expertise, maybe quickly you can tell us a little bit about how we work with clients and why clients actually work with Prescouter.
Absolutely. Thanks, Dino. And welcome to all of you. Good morning, good afternoon, good evening, depending on where you are. Very excited to speak with all of you today. And indeed, we're excited to also showcase Prescouter. Prescouter provides custom intelligence on demand, customized global research, where we act as an extension to your in-house research and business data teams, providing a holistic view of trends, technologies, and markets. We understand that research time and resources are limited, and so we can operate as an extension of your in-house teams to quickly get you up to speed in nearly any industry, any topic, any technology area. Our work allows our clients to increase their reach and bandwidth, save them time and money, and provide a global perspective in terms of key trends, new technology, and product development efforts occurring around the globe, as well as answering strategic, market, and R&D related questions.
Right. So, and what do you think makes Prescouter kind of distinct and different to kind of other types of resources and consultants that are out there?
Well, we have a few differentiators, but I would say that the number one thing is our in-house network. So we typically rely on and incorporate subject matter experts into each and every one of our engagements. We have custom capabilities to recruit and bring those on within a 2 to 3 week time frame for any topic and technology area, ranging from cryptocurrency and quantum computing to sustainability, materials development, and gene therapy, and everything in between. And so our access to experts, but also our ability to get in touch with potential partners, stakeholders at different organizations really allows us to get non-public information, get deep insights, and get you up to speed quickly on different areas. And we've heard time and again from our clients that it's something that they are not able to do themselves, and that really differentiates us from a lot of other similar companies.
Right. And we're fortunate today to have two of those kind of experts joining us. So I'll kind of hand it over to you to get our session started. Thank you.
Perfect. Thanks. And we are very excited to introduce two such experts. Dr. Oren Gal is assistant professor at the University of Haifa, focusing on swarms and AI labs. He has done significant work, R&D efforts for motion planning, innovative visibility analysis techniques for complex environments, working for both commercial and defense-related organizations. He's worked on motion planning, 3D visibility analysis, navigation, and many other things for underwater platforms like UUVs and USVs, and really knowledgeable expert with all things related to the AI space. We're also very excited to bring on Dr. Marco Leonardi, who's a performance analysis engineer at ARM and an AUV expert with a focus on image processing and machine learning. He has worked for several years within AUV automation, deep learning, real-time systems, AI, and robotics. He's also the founder of XSmart AS, which is currently developing human-in-the-loop remote driving tech for entertainment. At the end of today's presentation, we're going to have a Q&A session where we'll ask the questions from the audience to our panel of experts that should allow us to either dive deeper or dive into other areas of interest related here to the autonomy topic. So please, you'll notice in the Zoom bar, there's a Q&A button. Please direct any questions you might have during the presentation. That we'll collect them and then ask them towards the end. So with that said, let's jump into today's topic. And we'd like to start by illustrating a few use cases. What does, full autonomy look like in different industry? How do these different types of autonomous robots with different capabilities work together? And what kind of vision can that achieve? And before we jump into some illustrations for examples in manufacturing, mining and aerospace manufacturing, we'll start with some quantitative numbers. Why is autonomy so important? I'm sure you've all heard many things about AI and autonomy and how it can change our world. But even today, we can see direct short-term high impacts to business organizations. For example, looking just within logistics types of environments, we can see that applying autonomous capabilities within your operations can decrease labor costs and operating costs by 20%. Typically, investments into autonomous technologies find a break-even period within 2 to 3 years, and those numbers all jump up, up to 40% cost reductions and increased efficiencies, looking at very specific use cases. And we're really still at the onset of integrating autonomy into our operations. And so you can imagine that as we integrate these more and more within operations, these numbers should have even more of an impact. So with that said, let's jump into the vision here. But before we do so, we just like to take a quick poll in terms of our audience. You'll see this pop up on your screen shortly. Is your company currently considering the implementation of autonomous technology? We'll give it maybe 20, 30 seconds for everybody to answer this question, and we'll showcase the results before moving on. Okay, I think we should be getting close to the 20, 30-second mark here. Not sure if we can already start showcasing the results. Well, it looks like, as expected, our audience is, a lot of innovators, a lot of early adopters. 75% of the audience has said that yes, you are currently considering the implementation of autonomous technology, and so, hopefully, today's presentation will help you better understand some of the challenges with making that happen. For those who have not yet considered or are unsure, maybe this webinar will provide other considerations to help you understand the importance of these advancements. So let's start with manufacturing. And what does this vision of the future look like in a manufacturing setting? Well, it might all begin with fleets of autonomous trucks and drones that bring in your raw materials. Those raw materials being cataloged and inventoried in a fully autonomous warehouse where autonomous robots, forklifts, robotic arms work together to sort, categorize, store, and monitor each item in real time, providing a lot more flexibility to your supply chain and your inventory managements. Those raw materials could then be moved to a fully autonomous production line where fleets of autonomous machines and robots work to bring components, finished subsystems and systems to create a final product, different robots achieving different functionalities from assembly to welding, painting, and even inspection. And the advantage of having a fully autonomous system is that all of this can be coordinated to have very minimal downtime, to ensure seamless operations, and also to provide you with flexibility, allowing you to potentially to manufacture many more different types of products and SKUs than you might in a more traditional environment. After production, you might rely on autonomous robots, leveraging machine vision for quality assurance and control to identify defects and continuously do this monitoring directly after the production line. Validated products could then be packaged and dispatched automatically with robotic packers, and also monitored via a centralized system that is choosing the most efficient routes for delivery. All of this is going to be monitored, overseen, and controlled by a centralized AI control system that not only monitors, analyzes, and directs each autonomous unit and process, but also optimizes the workflow based on different issues that may arise that are picked up by sensors. This might be integrated into a digital twin type of solution where the system may also do virtual tests and optimizations to understand how to relay the production lines to increase efficiency. And so here we see that, from intake of raw materials to production and delivery of products, autonomous robots find a very useful and high impact functionality to support manufacturing. And the value of autonomous robots goes beyond manufacturing. If we take a look at a very different sector, like for example, mining, we can see that seamless integration of multiple autonomous robots with key capabilities also has a high impact. Whether that's at the beginning of the value chain where fleets of autonomous drones are doing aerial mapping and exploration, they might be outfitted with hyperspectral or LiDAR imaging to identify ore deposits and plan out a new mining site. Once these are identified, then autonomous drilling rigs, autonomous blasting robots might set up in order to extract those key ores and raw materials, which would then be transported via autonomous hauling trucks or railways or drones within the mine to different processing centers or environments. Meanwhile, all of the equipment and infrastructure is being monitored. Things like predictive maintenance are being leveraged in order to decrease the potential for downtime. And safety and surveillance is also occurring in real time, once again, with drones, with machine vision and other similar tools to have a deep impact on increasing safety within that mining area. I'll do with a final example, a bit more specific here for airplane manufacturing. Similar to our first example, once again, we start with autonomous logistics platforms bringing in raw goods, components, and subsystems, which are managed in real time with these autonomous capabilities. Parts are then produced autonomously, and the QA process, once again, is being done in real time. But we see that autonomous platforms can also provide value beyond delivery to the customer. Maintenance robots and automation of maintenance, predictive maintenance can all be leveraged to extend the lifetime of these finished products and deliver additional value to customers and clients beyond the production setting. So if this is the vision of the future that we'd like to enable, where are we today and how do we get there? And so we'd like to start off by showcasing just a few examples of how the distinct parts that make up these visions actually already exist today. We talked, for example, about raw material delivery. And today, companies like Aurora and Volvo have already developed autonomous trucks for freight delivery that have a deep impact on the unit economics of delivery. Just these examples allow for a close to 70% increase in efficiency for good transport. It reduces time for transport of goods by 66%, 20-25% fuel economies. When we look at how this is achieved, well, it's about coordinating between a perception system composed of different types of sensors. If we're talking about autonomous trucks, for example, there might be a LiDAR system, a camera, a radar system, some hardware chips, which are all functioning together with a navigation system to provide localization and navigation capabilities. All of this being integrated together into one system through data and sensor fusion and software integration. So this is something that many companies are already working with. They've already achieved significant advancements, as we've highlighted in the previous slide. Looking at inventory management, today Amazon has developed Proteus, which is a cobot, a collaborative warehouse robot. Schaefer has also developed an automated warehousing tool that allows for optimized picking and storage. Boston Dynamics has their Stretch mobile robots, and all of these are already seeing deep impact across business metrics, productivity and cost reduction between the 20 to 40% range, decrease in order picking time by 30%, 90% reduction in error rates. And this is without seamless coordination with all of these other pieces that we showed in the original vision. On the production line, we now see new types of robots. For example, here you can see in the image Digit, which was created by Agility Robotics, which is a multitask humanoid robot that does things like moving totes, palletizing packages, estimating box volumes, monitoring the production environment, which can be seamlessly integrated with both other robotics and autonomous machines, but also with human staff. And Digit is currently being tested by Amazon and GXO in some of their logistics warehouses today. One example on the quality control and assurance side, Creaform has their MetroScan 3DR, which is an array of lasers and machine vision tools providing automated quality assurance, providing very high accuracy and resolution acceptance tests based on ISO standards. Is being applied already today in different production environments like the automotive space. You also talked about leveraging autonomous robots within packaging and dispatching lines. Here's one example by Lenco, a flexible automated packaging that allows for the packaging of up to 1,100 parcels per hour, incorporation with 3D scanning tech for fit-to-size packaging, allowing you to replace up to 20 manual stations and reduce box volumes up to 50%, always moving towards more efficient and optimized delivery of products to your customers. And there's more coming. A suite of companies have been developing their own humanoid robots, kind of like the Digit example that we showcased. Tesla has Optimus, Figure has their speech-to-speech reasoning robot, Boston Dynamics with Atlas, and Apptronic with Apollo. And these are already being used in the real world today. So Mercedes, for example, recently had to face some labor and staff shortages, and they started integrating these robots within their production environments to enable these use cases. So our analysis into autonomy here at Prescout are really focused on identifying different ways to improve the level of autonomy and make it more seamless at an operational and business level. And you can see here 8 key areas that need to be focused on in order to achieve these visions. These can be broadly segmented into 3 categories: hardware improvements, software improvements, and collaboration. On the hardware side, we're talking about incorporating more powerful and cutting-edge chips, which allows for enhanced decision-making at the edge or within the robotic platforms themselves. We can also talk about improving sensor technologies for higher resolution, for better data, which can then be used by the AI architectures to optimize key functionalities. On the software side, improving and advancing AI training capabilities with better and better labeled data, developing new algorithms to enable autonomous systems, leveraging virtualization and simulation to have even more training data and to close the gap between training and real-world applications, but also improving AI interpretation of those sensor results for real-time adjustments and obstacle navigation, dealing with unknown environments that are not so well trained. And finally, the last piece is collaboration. These are complex systems requiring a wide variety of different functionalities and use cases, and this is going to require collaboration between different types of experts, different kinds of stakeholders, and research institutions. So with that in mind, let's dive just a little bit deeper into limitations and requirements. But before we do that, oh, no, sorry. I think in about a slide or two, we'll have our next poll. We'll start with 8 key challenges and limitations that we identified in a public-facing research paper that we published a couple months ago, focusing on autonomous underwater platforms, which are highlighted here. First, you can see on the left-hand side, lack of data and addressing labeled versus unlabeled data issues. Training AI engines for complex tasks like object detection, like mapping and navigation in new environments, dealing with things like noise and interference requires a lot of data. And it requires appropriate data, one which emulates the environmental conditions in which these systems will be operating. And finding that data, labeling it accurately, and then training your AI systems to achieve this can be a complex issue to deal with. Complexity is, of course, a key issue here, whether that's with implementation of AI engines, but also dealing with other issues that arise from this. How do we keep the platform connected to, say, a central cloud platform in order to update objectives in real time and monitor things? How do we deal with environmental heterogeneity when, for example, if we're thinking of an underwater AUV platform, it might be, at one point in a shallow environment dealing with a lot of sand and corals and fish, and then other issues might be dealing with, much deeper environments where there's not a lot of visibility, a lot more turbulence, etc. Cost and time, having resources necessary to actually bring this forward does require an investment. But as we showed previously, there is a short break-even time, a high ROI achievable if this is set up in the right way. We're also going to be leveraging multiple types of sensors in order to enable these capabilities. We talked about having radar, LiDAR, machine vision. In some cases, you might also incorporate temperature and vibration data and other types of sensors to enable these autonomous capabilities. And so allowing for an AI architecture and system, which allows you to do multi-sensor utilization and logical coordination is going to be important. And finally, dealing with a variety of stakeholders, different types of customers, different types of internal business units and partners and research groups that all need to work together seamlessly to have one well-functioning platform. So with that said, we'll move to our next poll. Just like last time, we'll give it 20 to 30 seconds. What do you see as the largest limitation for implementing autonomous technologies in your business? That'd be cost, technical knowledge, lack of partners, or a lack of a clearly defined product fit. Okay, maybe we'll give it 5 or so more seconds, and then we can show the results. Okay. So it looks like it's pretty divided. Cost remains the top issue, followed by clearly defined product fit, then technical knowledge, and lack of partners. And this makes a lot of sense. Different organizations are going to have different challenges and issues to deal with, which is why we recommend cross collaboration, working with a lot of different types of technical and business experts in order to move that forward. So back to our presentation here. And next, we'll talk a little bit about how to integrate all those moving pieces together to actually develop a fully autonomous platform and dealing with some of these challenges. Our recommendation is not to start from scratch, but rather leverage existing advancements and innovations that are already available out there, whether it's in the open source domain or privately with different groups and partners to minimize the investment and time required to get to that fully autonomous platforms. This is going to be a complex effort that's going to require different types of expertise in numerous technical areas like navigation accuracy, integration with new sensors, electrical systems, new AI and software platforms, resolving mechanical and design issues. But doing this successfully might allow you to deal with the data scarcity issue, deal with things like connectivity challenges, improve designs and innovate in terms of architectures and new systems to meet rising industry interest and use cases like the ones that we showcased at the beginning of today's presentation. With that said, we'd like to move to a case study in underwater autonomy platforms. This is based on like, as I said previously, a research paper that we published, which is public facing and available for free for download on our website on underwater autonomy platforms. We worked with a leading defense contractor and several experts to get some of these insights. But we thought it might be a good example for understanding some of the issues that you might have to deal with as you develop your own solutions. First, our analysis shows that for underwater autonomy, a minimum investment of about $100 million might be required to take the current best performing state-of-the-art platforms to a fully autonomous platform. This is in order to deal with the challenges that we mentioned previously. And just to illustrate that more simply, just dealing with data is going to require a minimum investment of $5 to $10 million, not only to collect the data, but as I mentioned previously, to label that data. Um, some research articles that did an analysis for the costs and time and resource required to label data had an estimate of about $2.50 per image. And if you keep in mind that a high functioning, well-performing AI system is going to require hundreds of terabytes for data for task execution, that's going to be at least $5 to $10 million just to label the data. And when we're thinking about an underwater platform which relies on data like sonar data, which is still technically challenging, where there's not as wide a library of images as there might be for, say, autonomous driving platforms on land. You have to deal with other issues like overdrifting, noise, the presence of shadows, different impact from different underwater environments, which might change from one location to another. These prices and costs will increase further. Other challenges that need to be addressed when we're thinking about navigating underwater in aquatic environments, these platforms are pretty cut off. Signals don't transmit well through water, and so you have to think also about improving things like communication protocols, boosting the bandwidth, ensuring signal robustness, and reducing latency. In fact, a high-level analysis that we did showed that you might need to improve latencies by 30x at the minimum in order to achieve higher functionalities of autonomy within these platforms. And while these issues remain, industry interest confirms that there is indeed business interest and applications for these developments. When we did an analysis of the IP landscape focused just on AI for underwater autonomy, which is a very distinct niche within the autonomy field, there's been a 10x increase in patent outputs over the past 20 or so years across a variety of domain. And you can expect this number to increase even further when we look at other niches or broader areas related to autonomy. This really demonstrates that we're at the cusp of enabling all these platforms. There's going to be competition within these fields, and be able to navigate these challenges should allow you to differentiate yourselves from some of your competitors. Taking today's underwater platforms to full autonomy, according to our analysis, is going to require a jump in technology readiness level by 7 different levels. And keeping in mind that this is a 9-point scale, there's still quite a bit to go. And this is also why a high investment might be required to enable these use cases. Incorporating some of the latest hardware and developments can also help improve some of these issues. For example, you can see that some of the best performing chips today, you would require at least 25 of them to achieve the 1,000 or so trillions in operations per second that you might require for a full autonomous platform. And I know that improving 7 TRLs, seems exhausting, but it's really for full autonomy. And so what we've done is created a sort of matrix to help illustrate where we are today and what still needs to improve. And so you can see the y-axis of this matrix highlights the time and cost to develop. So this is the difference in technology readiness levels, and the x-axis highlights the required accuracy and resolution. And so we've color-coded some of the key functionalities required, and you can see that today we're in basically the blues and the greens. These underwater platforms can achieve simple, defined mission objectives like navigating from point A to point B, like doing an underwater map of a particular region. They can do obstacle avoidance. We're also starting to see the emergence of more comprehensive mapping, path planning, and navigation functionalities. So moving from point A to point B to point C while achieving other sub-objectives before moving forward. But we're still a bit further away. So object detection remains at the component validation stage here, because in underwater environments, especially, as I mentioned previously, there's a lot of noise. There's shadows. It might be difficult to see what is happening underwater, and so more data, better labeled data, better autonomous architectures might be required before we move to the more complex use cases. These are things like multi-platform coordination, where you might have swarms of small drones or AUV robots working together to achieve a particular mission or task. We're also talking about adapting to unknown environments. So, maybe the platform has only been trained to work in shallow waters, but it has enough capabilities to then apply its knowledge and learning and adapt immediately as it goes to new environments that are very different from those it was trained on. And then we can talk about full autonomy, which is still, as we mentioned previously, about 7 TRLs away. And so this approach really helps illustrate maybe a development roadmap to enabling autonomy within these kinds of platforms. In the short term for underwater autonomous platforms, our work with experts has allowed us to identify a few issues, and other challenges beyond those that we've identified also emerge in the short term. Improvements in other systems that are concurrent, like the engine, providing autonomous launch and docking capabilities to reduce operational costs. Dealing with issues like cloud-enabled communication underwater, and improving cybersecurity, as well as improving AI through its algorithms, through its use of more resolute sensors. So I hope that this short and very high-level presentation has helped illustrate the use cases, the path forward, and some of the limitations and challenges to enable underwater autonomy. With that said, we will jump to the Q&A part of our session. So if you'll just give me one moment here. And please feel free to add more questions if they come up. So far, it looks like we only have about one question from Pete Del Camara, who asks, it seems like proper change management is also critical. How do you think about change management to implement these tools and training? And maybe we'll direct this. I think both Dr. Gall and Dr. Leonardi can provide some insights here. Oren, do you mind maybe starting and giving your perspective on this question?
Yes, sure. First of all, thank you for the great conversation and for the survey and for the great talk. So I think that of course that this kind of changes demands specific capabilities of management in order to put into our organizations things like data science, AI technologies, which of course in some ways can be a threat of our organizations and traditional way of thinking. So we know that part of it have to be integrated with in the first steps with man in the loop. I mean, we need to do that very carefully in small steps. So it's not becoming, very fast and changing DNA of the organization to become AI-based organization. But I think that this kind of change management need to be really, really in small steps on one hand, and on the other hand, with small successes for the organization. So it will show the value of these technologies for the organizations and for the understanding that there are some fruitful objectives for these steps. I think that what I know from my experience that we need to do that with the key persons, with the CDOs, with technology people in our organization on one hand, and the other hand, we need to do that with putting demand in the loop and not being threatened by this technology for our organizations, and that can be a proper change management for these kind of technologies. Thank you.
Yes, so first of all, hello everyone, and thank you, Sofiane, for the nice presentation. So yes, I absolutely agree with Professor Gall. I work in big tech, and for example, in the company now, ARM, we have been, for example, forbidden to use ChatGPT to program for a very long time. So now recently we're starting to develop internal tools for AI in order to avoid AP pollution and things like this. So in general, every company has to really look very well before introducing AI and robots in the company, because yes, of course you have a great benefits, that's for sure, but there are a lot of risk that you need to take into consideration, especially as a manager. So for example, for the classic warehouse example, right? You probably you can reduce the number of incidents on work when you have like a robot picking up a very tall, heavy packet on the top. But at the same time, you need to be sure that the robot doesn't like hurt humans while it goes around. So all of this has to be taken very well into consideration, and you need to take your time to introduce such tools in your company.
Thank you both. Very interesting insights. I'll also just add one final piece. We've seen here at Prescott when dealing with a lot of these issues that fostering a culture of open innovation is very important to enable any kind of key change, and so that requires laying down avenues for communication that transcend hierarchies, having objectives that are communicated from leadership down to move towards these very aggressive objectives. And so I think that's also something to keep in mind with regards to fostering those kinds of initiatives. We have a second question here from Francis Poliquit. Are there any use cases where companies might want to build their own autonomous systems instead of buying one directly from a vendor? And maybe we can reverse the order here. Marco, do you want to start us off?
Yeah, so this I almost basically already answered in the previous question. So, for example, in ARM, so the company that I work with now doesn't work with underwater. We work with graphic processor units. It's very important not to produce IP pollution. So, because of ChatGPT, like it's trained on the web, right? Maybe it's trained on patents from another company, for example, Microsoft. And if we use that tool, it might introduce some code, some latches in the Verilog or something that has been patented by Microsoft. And then we have an IP pollution situation where if Microsoft find out that we use the code, then we could be sued and have to share the profit and all of this. So it's that's why, for example, the tools for coding, they are getting developed in-house, even if now they are starting to allow Copilot, at least also for programming in ARM. So yes, on this kind of tools, it's very important to have your own personal. But I'm not aware of other such a specific examples in the industry as well. Yes.
Oren, do you want to add anything to this? Any use cases also come to your mind?
Yeah, so I can say that in the as far as comes to, of course, for the defense-related companies, of course, that all these capabilities would like to be very sensitive, of course, of navigation based on data science, for autonomy and decision-making for swarms or autonomous vehicles. So there's no way that they're going to use some of the vendor capabilities. More than that, even though we know the LLM capabilities based on AI and ChatGPT, etc. Still, a lot of companies would like to be independent to other companies, especially if they got a sensitive data that they don't want to share and put in the cloud. So as long as you would like to, you got privacy problems with your data, or that you're a bit suspicious about sharing the data in the cloud, you won't be able to use any kind of the commercial off-the-shelf capabilities, and you would have to develop them by yourself, or being able to use them without any communication to the web or to the net. So that's and that demands a lot of capabilities inside the companies, and sometimes even taking something that's very close with the algorithms and developments, and do that inside your organizations. And that usually happens when it comes to healthcare companies, when it comes to tech with very sensitive data, with medicine or defense, where there are a lot of issues with the privacy and sensitivity and classification of data.
Thanks. And I think that the data privacy issue is definitely one which is overwhelming in terms of this decision to build, make or buy for the autonomous systems. Something that many companies are struggling with. Even here at Prescatter, we've been forced to build our own LLM, ChatGPT functionalized service so that we're only keeping our data on our own servers. And we've actually extended this service called Oxy to a lot of our clients, which are looking for this. I think another key issue in terms of make versus buy for autonomous systems is actually the niche nature of operations for different types of organizations. So if you're doing something very specific, there may not be a ready-made platform that you can buy in order to have those functionalities, and that might require you to build your own autonomous system. Thanks. Great question here. Next question around data. How different is the data that these systems need for training versus the data we might already be collecting for automated visual inspection, for example? And I guess we'll continue. We'll switch every time here, maybe. Oren, do you want to get us started here?
Yeah, so let me try to make sure that I understand the question. But the data that we are collecting and the data that we're using for training for, let's say, visual inspection. I mean, the one that we can simulate and the one that we can use for training, which is not real data from a real sensor, but kind of data that we're training and we're simulating using guns or using other technologies, would be very different than what we're gonna meet in the reality, in the experiments. So the data that the systems will need to be trained of must be the same one that the sensor is going to be meeting in the reality. I mean, otherwise we will get very different results because the sim to real in these capabilities is very limited today. It's very hard to put the physics phenomena into the training and into the really nature of the sensor, and a lot of disturbances and the environmental models that we cannot simulate very well. So I think that it would be very different if we're using synthetic data in order to create training data if we don't have enough data that we already collected from the real sensor. So I think that this is the key for the high success rate using data science methods.
Thanks. Marco, do you want to add anything to that? Maybe a potential connectivity issue. While we're waiting for him to reconnect, I think that training data and actual data does differ in many cases. So if you're thinking about automated visual inspection, for example, there might be new types of defects that emerge that you might not be trained for. Oh, yes,
sorry.
Marco, are you
Yes,
back?
sorry, Zoom blog crashed. Yes, so yeah, I work with some visual automatic visual inspection, and yes, of course, I mean, you have some, you are using for doing like automatic visual inspection, very simple AI tools like the classic feature extraction and SVM, like a basic MLP network, so very basic AI, very basic classification techniques. Sometimes, depends on the application, the data can overlap entirely. But on some other application, it might not. So I think it really depends on what kind of application and what goals you want to achieve. So in general, if the domain where the like a more sophisticated AI has to operate is the same as the one as the visual inspection tools, then it's probably do you need all that much more data set. Yes, you can do data augmentation and generate some new data, of course, out of it, but it might be not be needed actually. Depends.
Thanks. So we have about 4 to 5 minutes left here before concluding remarks, and we have a lot of really great questions which are emerging here. So I'll try to pick maybe one or two to end on. And I guess first I'd like to ask the question on the low and high hanging fruits in automation, because I think this is very important in terms of understanding a path forward, planning a strategy in the short, medium, and long term. So what are indeed the low hanging fruit, the high hanging fruit in automation? Is it data labeling and curating? Is it integration with human in the loop types of systems? And I guess this audience member would also, if you have any examples from the healthcare sector to highlight this. Marco, do you want to get us started here?
Yes, so I don't see the questions anymore, but yes, so it's about just commenting on what you said. So I also worked with for a small amount of time for a system which was about was in the elder care sector. It was a robot that was cutting blisters to make like a cocktail of medicine to give to a patient automatically. So in that case, we had the full control of the camera and the system, so we were able to get the data set as we wanted to. So in general, it's all about the quality and so having a very good camera and correct lighting. That's very important, and all the area where it should operate has to be clearly put, and you try to have it like to have in the database everything that can happen. So sort of to limit to not like make it speculate as much as you can. So, but as far as I'm aware, there are still no standard, for example, for AI use in the medical field. So I'm not updated on this. It might be starting to be something, but at the time there was none. So we were quite free to not apply to many ISO standards like that.
Thanks, Marco. Or any thoughts from your side?
Yeah, I think that today we get more standards that goes through the to the types of interfaces between systems, but we still don't get any autonomy and data science standard. But we're seeing a lot of work that's being done today from the point of view of STANAG, which are standards from NATO, or we're starting to see more standards that comes from the Trust AI or explainable AI capabilities, which are supposed to solve some problems of the explainability of AI field and the ability of decision makers to understand what the AI recommendations are and being able to approve that, which are very strong tools. So they're starting to talk about architecture of AI that will lead to these outcomes.
Thank you. From my perspective, if I think about what's low-hanging fruit and high-hanging fruits, well, I think, in this presentation, we highlighted a few of the low-hanging fruit. It's these independent systems and robots which already have very clearly defined tasks. And if there's a good fit between the tasks that are able to be achieved and your needs, then that might be easy to incorporate, to learn about how to integrate these within your own operations before maybe building your own system. The high-hanging fruit was which actually might lead to the most amount of benefits and improved efficiencies is what I think of as a systems level autonomous platform. And it's these visions that we highlighted initially, where you're integrating all of these pieces together to work seamlessly together. And so not only does it require you to work with all of those individual robots and systems, but then have an integration feature to monitor all of this at once and control it at once with, say, a smart or digital infrastructure platform, and then being able to iterate on that in order to have more and more seamless integration. And so I hope that those answers helped illustrate some of these issues. We're out of time for the technical Q&A session. I know we still have a couple in here. Please don't hesitate to reach out to us here at Prescouter with any additional questions. We'd be happy to have a short discussion with you as needed on any topic and see if there's a good fit with our capabilities. With that said, I also wanted to thank our experts, Drs. Gall and Leonardi, for their insights today, their support in helping us put this presentation together, and their work overall. So with that said, thank you all, and I'll turn it back over to our CEO, Dino, for some concluding remarks.
I want to thank also the experts who joined us today, and Sophion for taking us through this incredible presentation and question and answer session. I definitely learned a lot about what's going on in this field and what's possible and where things still need some work. So we want to conclude by mentioning our next session, which is on generative AI implementation. So it's been kind of maybe ChatGPT really launched everyone into looking at generative AI more closely, and that was at the end of 2022. 2023 was a lot of interest and fervor around this, and we at Prescouter have been looking very much at how we can transform our entire business to take advantage of this technology. We've also been working with a number of clients on how they can run pilots and test out the capabilities of this technology. There's been, we think, a lot of hype, but there's actually also some real practical applications of the technology where we internally are applying things to kind of boost productivity and really improve the capabilities of what we're able to do. So we thought it would make sense to kind of take a moment to review what we've learned in this journey, both within pre-Scout, but as well as with clients. And we think there's a lot of interesting things out there that perhaps folks are not kind of fully aware of in terms of what's possible and where things still need some work. So in May, we have 2 sessions, mainly because we know that we have an audience in Europe and an audience in kind of the North America time zone. And so we're kind of trying to experiment next time with having 2 sessions, one that's more convenient for the European folks and one for the kind of folks in the US side. So if you're interested in learning more about how generative AI can be applied, we'd love for you to join